Let me first start by thanking CST, BPCL, and also my session chairs for giving this opportunity to come and talk to you about low-level heat recovery. So we have heard yesterday, a few of my takeaways from the sessions yesterday was, it was really fascinating to know that the energy demand of the world growth, India is about 25% of that. So it's a substantial thing. Then we heard about how energy efficiency is important because the energy intensity index preferably should be below 80. I think that's what the refineries are targeting, and how to bring down emissions by reducing CO2. So we'll be discussing mainly about efficiency and how to increase efficiency by recovering waste heat. Keith Couch, in his presentation yesterday, talked about how do we understand efficiency, right? It was like carbon, water, hydrogen, utilities, emission, and these all acting together to reduce or optimize the capex. We do understand that the plot area and the time of implementation is also important, but here, let me talk about a level of energy which cannot normally be captured by process integration. My friend Abhijit will talk about, I think, about pinch analysis and all those things. So this typically is the heat, which is the cold utility of pinch. Means you have to reject at a very low level. Okay, so this presentation will have some forward-looking statement. It's like some predictive statement, and take it in that spirit, and we will go forward with that. So this was typically the level of heat that I was referring to, heat which is in the temperature range of about 140 to 80, typically 130 to 70 kind of temperature range, which is the air condensers. Basically in the refinery, these are the air condensers to which this heat is lost to air. And if you know, everybody knows that your refinery, this is a substantial amount of duty which goes to the air. And it normally cannot be recovered, but it's at low level because you cannot integrate it to the process. So let's see how we can integrate this low-level heat to the process. So typically, what we can do, we can either elevate that heat to a higher level, to a higher temperature level, so that we can use it in the process again. Or there is an alternative where we can use this heat and we can convert it to power. And organic Rankine cycle, this is nothing new. This has been in the industry, so you can recover the waste heat in terms of power. And whereas the other one is typically a heat pump, where you can elevate the heat, take it to a higher level, and then use it in the process. Very on a high level, this is what we intend to mean, like in a heat pump, in a MVR, which is also a heat pump, but is using a water or steam as a driving fluid, and then the organic Rankine cycle. So fundamentally, what is happening? There is a low boiling point liquid, which is kind of picking up heat from the process condenser, which is actually the evaporator in its case. It becomes vapor. So when you go into a heat pump, you are compressing this vapor, so you are utilizing energy from outside, electrical energy. So you are compressing this vapor, and if you compress a vapor, your temperature goes up. And then you use that temperature in some process reboiler or for process heating. MVR is a similar thing, means you use the process condenser and you generate low pressure steam, then you compress the steam to take it to higher levels. And you can take it to the levels you want it to, depending upon the number of compression stages and the power that will be required to drive it. As you know, that these are typically defined by something called coefficient of performance. So it's the amount of duty which you can give to the process divided by the amount of power which you use in the process. So typically, the higher the COP, the better the process is. On the extreme right, the organic Rankine cycle is also similar. There is a low boiling point liquid which is vaporizing, and instead of compressing it, now you use it to take the power out of it. So it will go through a turbine instead of a compressor, and it will give you power which you can either use in the process or you can put it in your grid, depends upon how you want to use it. So you can see that in both these processes, it's happening that you are using some kind of mechanical force, right? It's like a thermally driven mechanical process. So in one, you are using the energy to compress. The other, you are rotating motion of the turbine is helping you to recover the heat in terms of power. UOP has been doing heat pumps in its technologies, in many of its technologies. And typically, as a rule of thumb is, if you have two components in a column which is boiling pretty close to one another, maybe a difference of 1 or 2 carbon number, then you can maybe use the condenser heat and then compress and reboil it. So what you do in the process, you actually save the steam. Because generation and steam leads to emissions and is not that very CO2 friendly, CO2 emission friendly. So you are cutting back on your steam import or steam generation, and you are using the process heat itself to reboil. And it moves, obviously it will move in a loop, it will condense, come back, and again go in the same thing. MVR, as we talked about, is steam doing in this process. Instead of a low boiling fluid, it is water which is moving around, and it is getting steam, compressing steam, and then coming back. Organic Rankine cycle you are generating power out of it. But one important thing here is you are limited by the thermodynamics, so you are limited by Carnot efficiency. You can't exceed that for any reversible engine, as you know. So lower your sink temperatures, means the lower your cooling water temperatures, or you can reject the heat at a lower level, you will get more efficiency, because that is how the whole process works. We heard a lot about innovation yesterday, right? So these processes, although are effective measures to improve your efficiency, it uses some mechanical element in it. So, and it is known, but the way we use it for process is something which is different. Now we heard about innovation. So here is something where it's a novel, innovative technology. It's called Q-pinch. It is developed by a company in Belgium. And now UOP and Q-pinch has an exclusive alliance. So, which leverages kind of UOP's extensive experience in technology development, licensing, design, and then our expertise in modularizing and using the global network of customers which we have. So these two in combination, we are bringing this technology to our customers. So what does it do? Now, fundamentally, it's a very simple thing. It's like a phosphoric acid solution which is moving in a loop. So if you see the cold reactor, it is nothing. The first step is an endothermic reaction which happens. That means it takes it in from the process. So your waste heat, which is at low level, will be taken in the endothermic reactor, and phosphoric acid molecule will dimerize. When it dimerizes, it releases water. So it's an endothermic step, it dimerizes, it releases the water. The water which is separated is then heated by using a part of the heat from the waste heat itself, which is coming from your process, and is converted to steam. Now the dimer is taken to the hot reactor. We call it the hot reactor. And this steam, when it contacts the dimer now, the reverse reaction takes place. That means the dimer breaks into the monomer, and it releases heat. So because it releases heat, the temperature level goes up. So what we saw in the last two, that it was thermal and mechanical. Here you see that's a thermal process boosted by chemical reaction which is happening. So this is what it is happening. Means in the forward direction, the endothermic step is two molecules combining, releasing water, and the exothermic step is it coming back to the monomer again. So it is moving around, and it is increasing the level of the heat by the heat of reaction which is happening in the whole process. It looks pretty cute and pretty innovative. But the next question is it simply on paper, or we have something running right now? So as we speak, it's a very flexible energy. And because one of the main criteria where it is outweighs the other technologies is that you are putting in, suppose you are putting in 10 megawatt of waste heat, you will be able to get about 5 megawatt out of it. So slightly differing depending upon cooling water temperature and the conditions. So 45 to 50% efficiency No other waste heat recovery process can give this amount of heat recovery within the process. 80 degrees centigrade, you will get the hot reactor output at about 120. So, by the way, the hot reactor output as of now is in terms of saturated steam. So, you generate saturated steam, and so for example, if the inlet is at 120, if we get a relatively high temperature steam, it can give you a temperature of 200 degrees centigrade. So higher the inlet, higher the outlet goes up. So 200 degrees centigrade will be about a saturated steam of about 15 bar or something like that. So that is how it can boost up the entire process. So as we talk, there are units already operating, although in Europe, but the one which you see on your extreme left is for a LDPE unit. It's in Antwerp, Belgium. And you can see that it picks up heat from different sources. So it picks up heat from one source at a time. It is so flexible that you can change it to another process. So you can see, depending upon the inlet temperature, the pressure of the steam at the outlet is varying. Because the inlet temperature less, the delta is a little less, the inlet temperature goes up, it goes up. The second thing, it's also, it's called ethanol vinyl alcohol copolymer plant. It is also in Curare, it's in Belgium, and it's same kind of 1.3 megawatt. Here, there are two columns from the condensers of which this is picking up heat and then giving the heat back to the reboiler of the column. By doing so, it cuts back on the energy requirement by 50%. So you can imagine 50% of the steam can be backed off, is no longer required. It's self-sustaining. The third one is one we are really very proud of. It's kind of our demo unit. We are doing all the improvements in hardware, software here, and we can emulate customer design conditions here and can show you the lift which we can give for a particular process, and customers are welcome to visit this plant. It is in Belgium, but in a different site. And we are also working with global customers now to go to different refinery processes and use this to recover the heat. Typically, this is the one I was talking about, picking up the heat from the overhead condenser and then use it in the reboiler. Now, although it is illustrated for this process, you can well see that it is not limited to this process. It can be used for other things also, other processes also. An example of how it is done in traditional refining, this is a hydrocracking unit. You can see the different sources of heat from which it picks up. And again, you see that instead of about 22 megawatt inlet, you are getting about 11. So kind of 50% of the heat is available. This is for a renewable jet fuel unit. And so it's kind of process agnostic, means as long as the waste heat is there, it can use it. It can use it. It depends on how we configure the heat pickup. And then you need to have a heat sink. That is very important. Means you can pick the heat, but where to put it. So that needs to be identified. And we are more than willing to work with you. So it's kind of a very simple kind of questionnaires which we work, and we do the initial screening, which will work with you to develop the project. And as Matt said in his plenary session, that be bold and take and adapt new technologies, right? And we are there to work with you at every step. So with that, I think thank you.